Hello, welcome to this is a coding challenge. This is a coding challenge. The coding challenge today, right now, is a binary tree. Okay, that's what I'm doing. It's actually kind of an interesting thing. So first of all, I've been reading this book recently. I just finished it called Grokking Algorithms. It's great by I'll put a link to it it's by Aditya Bhargava. I'm sorry I pronounced that wrong. I'll put a link to it in the this video's description, and it's been refreshing my brain about all these algorithms that I may have once learned and then never really bothered to use again, even though they are vital and important. But what I really want to ask in this series, because I'm going to have a bunch more related to this sort of similar topic, is what kind of creative outcomes can you have with this? So I'm going to come at this from a very no point of view approach. Let's just look at the literal binary tree algorithm. Let's make a version of it. I'm actually not going to include any visuals. I'm just going to show you the results in the console, and I'm going to ask you, the viewer, to make some type of visual out of it or to do something more interesting with it. So maybe when I get to the end, I'll have some ideas for you because I don't have them right now. So look, I have all these pictures of binary trees behind me, and let's go over here to the whiteboard and let's make a diagram. So why would you need a binary tree, first of all? And actually, this is the example that's in this book, so I'm going to borrow it. Pretend this was a phone book. It's not a phone book. But it's a big book. It's a book of random numbers. That's another story for another time. And let's say I wanted to find where I am in this book. By the way, do you even know what a phone book is? I just said, pretend this is a phone book. People of the future, aliens of the future. A phone book is a book. I'm speaking to you up there, not you. Hold on. People of the future. A phone book is a book with people's names in it and everybody's phone number. Oh my God. A phone number is a sequence of digits that you use to call somebody on a phone. A phone. Let's just, I don't know how far into the future you are. Hopefully you still know what a phone is. Anyway, let's say this book was a list of people. Dictionary, maybe dictionary. It's a dictionary. A dictionary is a book, I don't know. List of words. And I want to look up the word rainbow or train. Pick your word. One way I could do is I could go to the first page, and I could say, oh, apple. And I could look at every single word on the first page, it's not there. And I could look at every single word on the next page, it's not there. And I could look at every single word on the next page, it's not there. But I know rainbow is R, which is going to be, somewhere around in 2/3. So I have a sense of where it is. But another way I could look is I could just go straight to the middle. And I could say, is the word that I'm seeing here now, does it come before or after rainbow in the alphabet? If it becomes before, if it becomes before, then I'm going to go halfway towards the end. Then I can go halfway back, then I can go halfway again. So I could keep finding by dividing all the words up in half. I play this with my kids all the time. Let's guess a number between 0 and 1,000, and I'll always guess 500. And they say, well, it's too small, so I'll guess 750. Well, that's too big, so I'll guess whatever's in between those two. 625? I don't know. 675? Oh my God, I can't do the math. So the point is, a binary tree is a data structure that allows you to move through sorted data by dividing it in half. Now, there's a lot more to the efficiency of the binary tree beyond that, but let's just start by designing one and come back to some of these questions later. So first of all, what do I mean by data structure? Here's a data structure. var x equals 10. My data structure is a single number. Here's another data structure. var nums equals 10, 11, 12. This is an array. It's a list of information. There are, I can have an object in JavaScript, which is a mapping of keys and values. Favorite color, whatever, purple. So these are different kinds of data structures that you're familiar with. It's a structure where you store data. And we could get fancy about it. There's things like linked lists, which each object, each thing points to the next thing. So you can only get to it from the beginning by going through all of them. And boy, I should make some other videos about all these things. And there's stacks and queues and all this stuff. A binary tree is a data structure that works like this. There is this idea of a node. This is a node, and I'm going to call this node the root of the tree. And it has maybe a child, two children nodes, one the left one and one the right one. It's a binary tree because each node can only have two connections, two children. Other kinds of trees can have all sorts of variable amounts. Here, here, here. So it looks like this. Now, this is the way the data is organized. But I said the data is sorted. What do you mean? That doesn't look very sorted. I mean, I could imagine this being sorted. Well, strangely enough, it's sorted in quite a remarkable way. And the way that you build a tree is by adding nodes to it one at a time. So let's use numbers. Somebody shout out a number. There's nobody around. I can't get anybody to give me a number. Oh well, I'll have to think of one. There's a chat going on, but I can't see that far from here. So let's say I have the number 10. I'm going to add these numbers: 10, 5, 15, 7, 2, 9, 31. This is a list of numbers that I just sort of thought of in my head that I'm going to add. So I'm going to add to the tree first 10. So 10, the tree is empty, so the root node gets the number 10. Now I want to add 5 into this tree. And right now the root node has 2 empty spots. As soon as I make a node, it gets 2 empty spots. Now 5 is coming in here. And I believe if 5 is less than, it should go to the left. And if it's greater than, it should go to the right. Boy, I hope I'm doing this correctly. There's, obviously it could work either way, but there's a standard. So 5 is less than 10, so it's going to go here. And now this has a left and a right with nothing. 15. 15 is more than 10. It's going to go over here. And this has a left and a right. 7. 7 is less than 10, so it goes over here. Oh, 5, it's greater than 5, so it goes over here. And now this has a left and a right. 2. 2 is less than 10, 2 is less than 5, 2 goes over here. I can't keep track of the way that I'm using dotted lines or not. So this, okay, we got to get through the whole thing. 9. 9 is less than 10, it's greater than 5, it's greater than 7. 9 goes down here. 31. 31 is greater than 10, 31 is greater than 15, so 31 goes here. So actually, I don't know, just sort of erase these. These are all the empty spots. So this is the tree. So how is this sorted? Let me tell you something. This is most certainly sorted. It's sorted because if I go all the way to the left, watch this. Let's go to the left, 5. Let's go to the left, 2. Let's go to the left. Oh, nothing left. Let's put out 2. Now let's go back. Okay, 5. Oh, now let's try, sorry, go to the left, go back. Now we try to go to the right. Sorry, go to the right. Nope. So let's come back, go up here, 5. Now can we go to the right? Yes, 7. Go to the right, 9. Actually, sorry, 7. We should try to go to the left. But we weren't able to go to the left. So we came back, 7. And now we go to the, This is so hard. Let me do this again. I don't know if I should edit this and come back. But the algorithm of how we traverse this tree is we want to visit every node. Visit a node. And when we do that, we want to go to the left, which means that means visit the node to the left. So we're going to implement a recursive algorithm, a recursive function, a function that references itself. Visit a node, go to visit the, and so I should say, start with the root and then visit left. So we keep visiting left all the way as far as we can. Eventually we can't visit left anymore. So then we might say, print, I'm just going to say print the value. So we come up and print the value 2. What's the next thing we do is we visit the right. So now we go down here. Oh, there's nothing there. So we come up here, and then these are finishing. Where were we here? Now we've finished visiting 5, so now we print out the value 5, and then we visit right, 7. What do we do when we visit 7? We then go to the left. Nothing there, so we come back and print out 7. Then we visit the right. Then we go to the left. Nothing there, print out 9. Go to the right, nothing there. Back, back, back. Here. Then we print out 10. Then we go to the right and we try to go left, nothing there, 15. Then we go to the right, nothing there, 31, and we're done. So this tree, magically, the way that the things are added to the tree end up in sorted order, because what we're doing is we're basically saying, I want to look here. This is how it ties back to that phone book example. Oh my goodness, can't believe I missed this. If I want to find the number 9, right? Let me find the number 9 somewhere. Like I want to find this name in the phone book, because the number 9 might be associated with some actual important piece of information we need. The 9 just being like a key. I can say, is 9 less than or greater than 10? And if this tree is balanced nicely, meaning there's the same numbers on the left and the right, I now have eliminated. I don't have to search through half of the data. Whereas if I have an array and I need to try to look through the array to find something in an unordered array, I have to check every single option. So this is the structure. How do we program this? This is the next step. Okay, so back over here we can see all of these nice visualizations of trees. Maybe I'll try to add a little visual something just so you can get, would you get started with visualizing it? But hopefully that gives you an idea of what it could be useful for. Talk about that. Okay, so now let's start to program this. So what do I need? How would I even get started programming this? Well, think about this. I think I'm definitely going to need a node object. So I'm going to write a constructor function called node, and it's going to have a left and a right. And I'm going to set those equal to null, just to sort of explicitly say when I make a node, and the node should have some kind of value or label. I guess I'll just use numbers. Maybe I should use text. I don't know what's better. But let's call it a label. So I'm going to make, it's like the sort of data at that node. I'll call it value. Right? So when you make a node, it has a value and it has a left and a right, which have nothing connected so far. Let's make a tree object too. I don't know if the tree is really going to need anything, but a tree is going to have a root node. And then also, so that when the tree starts, this dot root equals null. So the only thing, one of the things that's interesting about this data structure is I only ever need a reference to the root. If I have a reference to the root, by moving throughout the tree, I can find any element. Okay, so what happens if two numbers are equal? We'll get to that. That's a great question. Okay, so what do I want to do? I need a function. I'm going to use prototype to attach functions. So I want the tree object to have a function called addNode, and it gets a node as the argument. And the first thing I'll do is just say if this dot root is equal to null, then this dot root equals n. Great. So then let's say node n equals a new node. Well, let's use numbers for right now because I think that'll be a little easier to see. 5. And let's make a global variable, just tree. This should probably be called binary tree, but tree equals a new tree. Then I have this node and tree.addNode n. Okay, so and then let me just say console.log tree. So let's see. So this should be, so by the way, I'm using P5 here, but there's actually nothing about this that I'm using. There's nothing here that I'm using P5 other than the setup function. I have no canvas in there, so it doesn't draw a canvas, but I'm actually going to probably out. And I have an error, someone just pointed out. If this dot root equals null, if I want to test if it's null, I need a double equals. And if I really, really, really want to test, I could use triple equals. Someday I just want to make a video only about double equals versus triple equals. Which is such a funny little concept. Maybe I should do that before I leave today. Okay. There we go. So now let's run this program. Where am I here? Uh-oh, I have an error. Sketch.js line 1. Oh my goodness. I've been programming in too much Java today. This should be var tree, right? I don't need to give it a type. And this should be var n. Boy, I was programming in Java earlier today. You can tell, right? Okay. Oops, wrong thing. console.log, not capital tree, that particular object. There we go. So we can see the tree has a root and it has a node. The root is a node with a left and right being null. Perfect. Okay, here we go. So we're in pretty good shape. Now what happens if I create another node? And you know what, you're right, I don't really need this variable here. I can just do this. I don't need a separate variable. I can just say add a new node. I could also, if I really wanted to, what if I just to make things a little simpler, I'm going to say add a value 5. And I'm going to have this function create a node from it. And so this is really the same sort of thing. But this is just a little simpler now because I can have that function take care of that. OK, so what happens now if I say add value 3? Now, first of all, was I right that things that are less than go to the left? Let's go back to the browser, that binary tree. Yeah, it looks like these examples. Uh-oh. Whoa, I don't know what this is. Oh boy, I don't know what's going on with these binary trees. What? Yeah, this looks right. So less than goes to the left. Some of these images are doing something slightly different than what I'm doing. Should not rely on Google image search. OK, let's go back to my code. So let's say I want to add node. OK, so I have another error. This needs to be add. I changed this to add value. Maybe I should just call it add, but whatever. So now what do? If root is null, it should be the root is that node. So what if root is not null? So what I need to do is say this.root add value. So really what I should do, this is interesting. This.root add value. Okay. Listen to this. This is crazy. So I actually, I'm losing my mind here. Okay. Otherwise, here's what I want to do. Otherwise, I got it. This.root add node. Sorry. Add node n. So, okay, what am I doing here? So what I'm doing is I want to say if the root is empty, just set it equal. But what is this function? This.root add node. This means I need a function as part of the node that knows how to add something to itself. Oh, this is great. Right? So I need a node function, node.prototype.addNode equals function n. So that's the node that's coming in. Now, what happens if I'm a node and this comes in? Well, I want to compare the value of n. If n's value is less than my value, then this.left equals that node, right? It should be, so if I'm adding it to myself, if it's less, it should go there. Otherwise, this.right equals n. But this isn't correct. This is a nice idea, right? And it will work for just the root, because when these two things are empty, it will get added here. But what if it goes to add to the left, but there's something already there? Well, it needs to check against that one, and in that one, it should then go to the left. And it should check against that one, and then maybe that one should go to the right. So here's where I need recursion. What I actually want to do is say this.left add node n, or this.right add node n, right? Because I want to just say keep going. But what if this .left is null? So if this, there's probably a more elegant way to write this. If this .left is null, then it should be that value. Otherwise, keep going. Same thing here. If, if this dot, I see a lot of chat messages telling me I'm doing something wrong, so I'm sure I'll discover that in a second. If this dot right equals null, this dot right equals n. else addNode. Line 17. Var n. Okay, big deal. That was all it was. Because I keep writing node. Okay, so I don't think I have anything. Hopefully, I don't have anything majorly wrong. Now, I'm sure there's a way we could write this. We could refactor this to be a little nicer. But it is saying exactly what it's doing, right? If this value should go to the left, if the left is empty, perfect. Put it there. Otherwise, recursively go and call that function again. Otherwise, if it's go to the right. Now, here's the thing. If it's equal, I kind of want to do nothing right now. So I think what I'm going to do with equal, if the node is equal, it just shouldn't go anywhere. And so in that case, I can say else if n dot value is greater than this dot value. So actually, in the case of those two values being equal, nothing will happen. So an equal value won't get added to the tree. Okay, so let's take a look at this. Okay, let's run this. Let's run this. So the tree has a root which has a value of 5, and to the left of it has the value of 3. Boy, this is a really awkward way to look at it. So we're definitely going to want to visualize this in some way to see if what we're doing makes sense, but we can see that this is correct. Now, if I were to then say, add the value. It's weird that I console logged it later and it was there. Add the value 7. Let's try that. The tree has a root, and the root has, if I zoom into this, the root's value is 5, the left's value is 3, and the right's value is 7. That's exactly right. Let's just try one more thing. Let's just, I don't know, let's add 6. That's a little bit tricky, right? But it should be, 6 should go to the right of 5, to the left of 7. So let me refresh this again. The tree has a value of, no, the root has a value of 5. Left is, has a value of 3, sorry. Right has a value of 7. And to the left of that has a value of 6. So this is no way to understand or see. This is like, I'm kind of used to this weird JavaScript console, but the tree is there, right? And only thing I need to know is the root. So remember how I said, okay, well, what if I want to then look at all of the values? Or what if I want to search for, I mean, the whole thing was this is like a binary search tree. The idea is we're storing all this information in this tree. I could search for something in it. So how do I traverse the tree? How do I traverse the tree? So let's just look at how we would traverse the entire tree. And this is exactly it. I want to start by visiting the root. And when I visit the root, I visit the left. Then I print out its value and visit the right. But that's done recursively. So visiting the left means visit this left, means visit its left until there's no left, then come back, then print out the value, then visit the right, etc. So this algorithm that we worked out, it's very hard to hold this into your head. So recursion is new to you. I think I have a video where I go over it and look at like factorial, in fact, the math, drawing some like recursive trees and fractal patterns. You might look for some of those videos. But this is a tricky thing to get. So let's create a function now that's part of the tree. Prototype, I'll call it traverse. And it is a function that says root.visit. Wait, is this right? So what I want to do is first visit the root node. Okay. And then in the node, you know what I need to do now? I need to make some separate files. I'm going to make a file called tree.js, and I'm going to make a file called node.js. Oh boy, is that a problem? Node.js. So if I go to Sketch, I just want to be able to pull this code out and look at it on its own. So tree just has these 3 functions now, the add value, the traverse, and the tree. So the tree is just really a wrapper for the root. That's all it kind of does. The node is where all the sort of guts of the algorithm is. So I want to take all this node stuff and put it here in this file. And here we go. So now all I have is so far is the constructor to create the node, which has a value and a null left and right, and then this addNode function, which recursively figures out where to keep going through more and more nodes to where to add it. Now what I want to add is a function called visit. And what does it mean to visit? This.left.visit, this.right.visit. So I always want to go to the left first, because I want the lower values first, so that was definitely right, and then I want to visit to the right. But in between, if I go all the way down to the left, if I want to actually do something, I want to process the value or check what it is, here's where I would say console.log this.value. So here's the problem is, though, I don't want to say this.left.visit if it's null. So only if this.left is not equal to null. And I know I could, in JavaScript, I could just say as long as this.left exists, but just in case, it could have the value of 0, which is going to cause me a problem. So I'm gonna stick with checking to make sure it's null. And if this.right does not equal to null, this.right.visit. Okay. Look at this. So simple, beautiful, elegant. I love this kind of stuff. Line 7, I have something wrong on line 7. Node.prototype. Thank you. I love having a chat that debugs this stuff. Okay, so here we go. I think I just sort of typed this from scratch. Could this possibly really work? So let's now, let's go here and see if in the sketch, I'm going to now say tree.traverse, and I should just see all the values in sorted order. Okay, tree is not defined. Oh, of course. I always do this. I forgot to add a reference to these two new files. I just invented a whole new JavaScript library called node.js. Not really, tree.js. There's a whole big server-side JavaScript programming framework called Node, so I feel like it may be a little bit weird that I called my file node.js, but we'll live. Okay, root is not defined. This dot, son. I forgot this dot, clearly. Did I forget it anywhere else? I don't think so. Let's run this again. There we go. Look at those values. 3, 5, 6, 7. Okay, let's try this in a crazy fun time way. Because hasn't this already been so much fun? Let's say for var I equals 0, I is less than 10, I plus plus. Let's add a random number between 0 and 100. And I'm going to floor it just so it's integers, even though I don't really need to. And I'm going to console log the tree and say tree.traverse. So instead of hard coding the numbers, I'm going to pick random ones. And let's run it. These look sorted. These look sorted. These look sorted. It's great. And let's add 1,000. Yep. That happened pretty quickly. So, I mean, we'd have to. Now, here's the thing. Let's go back to just doing this with 10. Let's look at the actual tree. The root has a node to the left, which is 68. No, the root is 89. To the left is 68. To the right is 93. See, again, this is no way to look at it. So we're done with the binary tree. I didn't actually add a function that is that involves searching the tree, which I probably should. That would kind of make sense. So we could search. So we could add that. Let's add that. Let's add a function that searches the tree. And it's going to be very similar to traverse. So we're going to say tree.prototype.search equals function. I'm going to search for a value. And we're actually just going to do the exact same thing. Oh, sort of. We're going to say this.root.search for val. So again, the tree object is just a wrapper for the root. And we're going to say search the root. So now this visit function is going to be very useful because we're essentially doing the same thing. But what we're first doing is we're first saying, does this dot value equal val? Right? Then I want to say console log found plus val. And then Otherwise, if this dot value is less than, no, sorry, if val is less than this dot value, then and this dot left is not equal to null, then I want to, go and search for that value here. And then I'm going to do the same exact thing for the right. And I'm going to search for the value to the right. So this is how I could just say, hey, is the root the value? No, but I'm less than it. So just let's look at everything to the left. So I don't need to, I'm not traversing the whole tree. I only need to go the one direction that I need to go. So insert one direction music right now. Okay, so let's do this. Let's see if this works. So this is what's in the tree right now, all these numbers. So if I say tree.search 53, this .root search is not a function. What did I do wrong? I called it visit again. This should be search. Let's do this again. So I want to say tree.search, let's look for 61. Found 61. Can you guys see this? Refresh this again. Well, you can't see at the bottom there because it's cut off. So let's do this. Sorry, hold on. So let's do a tree.search. Let's look for something that's not there. So 9 is not there. Undefined. So that's pretty good. I probably should have something where, I mean, that's fine. I might want to explicitly somewhere say at the end return undefined or return not found. But I can basically say here now in my, wherever I, you know what? I should just return. So that's what I should do. Sorry. Right when I found it, that's what I should do to make more sense. Right here, I should say return, I might as well return the node. Return this. So I found it at this node, so I'm going to return the node. And then at the end, I believe if I just say return, null. So if it never finds it, eventually it's going to recursively percolate through all these functions to get to the end and return null. I think that's right. So let's do this again. So now let's say tree.search for 20, which I know is in there somewhere. And, I got undefined. You know what? This is not the right place for this. Because, right? Because it could be, because it's equal? No. Vertical bow tie mode. Wait. Let me take this out for a second. I have to think about that. Tree.search 4. Undefined. What's wrong here? What did I miss? Return this. Console.log found val. Whoa. This should say var found. I don't know why I didn't have this in. I didn't add the part. I'm really sorry, everybody. My brain must have just melted. Var found equals this. So if found is not equal to null, console.log, found, and then I could put that object out. Otherwise, console.log not found. I don't know why I missed that. So we're searching. Okay. So now I should say tree.search 10. Found 10, not found. So why does that happen? Why does that? Oh no, it didn't. It found it, but it said not found. What am I? My returns is all. My return is all messed up. Let's think about this. Boy, this is hard. search, found. Oh no, I'm in the wrong place. Oh, I'm in the wrong place. This is where I just haven't really thought about what I'm doing. It helps to think about what you're doing. What am I doing? I want the tree. This is the function I'm calling. I want this function to return something. It's printing out the right thing. The whole point of this is not to print something out, but to return the thing that's found. Return found. That's all I need to do. Forget about all this. I want to return found because I want to see it in the console. Somewhere else I might call it. So I just kind of like got confused because I'm typing everything into the console, which is a little bit confusing. So let's run this again and say tree.search 19. And hold on. Did I not save everything? Okay. Of course, the problem is if I want to return a value, one of the nice things about this visit thing is I was just going through everything. I wasn't worrying about returning a value, so I would just call the next function. But if I want to, I need to return the results of the recursive calls. So I need this return, and I need this return. So this should really fix it. So I'm going to refresh this. Now I'm going to say tree.search 12. And now I've got 12. But as I changed it to, but I want to, let's return a reference to the full object. Doesn't really matter. But tree.search 5. And we can see I got the node now, which has the value 5. I know this laptop is kind of covering it. So that's how you search the tree. And if, by the way, I search for something that's not in there, I'm going to get undefined. However, I can put this back in just to be sure, and I can get null. So if what I want to do is, now actually here I could say, tree.search, 10. Let's just see if this tree has 10 in it. And I could say now if result equals null, console.log, not found, else console.log, result. So now I'm going to run this, and 10 is not in there, 10 is not in there, 10 is not in there. How likely is it it's going to put 10 in there? Oh, it had one that found 10. So, about 1 out of every 10 times there, I can't stop hitting refresh. Stop, find it, find it, find it, find it, please, find it. Oh, come on. Oh, no, what's wrong with me? Okay, you guys get the point. Okay, so this is a binary tree. Woo! Hopefully what you've seen now, just to summarize, I think I'm going to, in a separate video, make a part 2 where I just add some visuals to it. But that's what I want you to be thinking about. Well, why would you? This is an important data structure that you can use to store information for binary search, for sorting, for dictionary of words. There's so many possibilities. But the key thing is, what kind of creative outcomes could you have here? Could you create some type of game which involves a binary tree and you have to add things and find things? There's the sort of Plinko thing I made before. Could you make a binary tree where added some physics to it? Just visualizing it. Is there something beautiful in the way that the binary tree, you traverse the binary tree recursively? Could you do some kind of nice animation? I think there might be some unique possibilities there. So I'm not very good at this kind of stuff. Any of it really, but especially the visual stuff. But in the next video, I'm going to at least try to draw some of the tree so we can see how it looks if we draw the sort of basic elements. Okay, I'll see you there.